In the last 3 episodes, we built the path model. We built the congestion model. We debated what congestion actually means. Now we test everything against reality. Packets tell the secrets, Wireshark listens, and you see the truth. I'm Tai Fung, and welcome back to my network analysis class. So how do we use Wireshark to make the packets confess, to see through to the essence? Here's the thing. This model isn't just theoretical. It's a tool you can touch, see, and use. The network congestion model visualizes the key parameters that affect network performance. It allows you to clear the mental clutter and grasp the essence, even in a complex and dynamically changing network environment. No matter how complex the network structure, you can use this model to identify traffic characteristics and problems. But the prerequisite is being able to skillfully analyze its manifestation in actual packet captures. Let's look at how the core parameters appear, or can be calculated, in Wireshark. For this demonstration, we use an example, as shown in the graphs on the right, with a fixed bandwidth and a fixed buffer size, which is set relatively small, 0.3 times the BDP size. This ensures that after packet loss, CWND drops below the BDP, allowing us to clearly observe the complete three-phase process. Round trip time, RTT, visible in the RTT graph. Base RTT is flat and stable as long as the path remains unchanged. When queuing starts to form, RTT begins to exceed the base RTT. Queuing delay, RTT increases when queuing starts to form. From this point on, RTT equals base RTT plus queuing time. Its dynamic changes can be visually observed via the RTT graph. For scenarios with fixed bottleneck bandwidth and buffer size, the max buffering time of this buffer can be observed and calculated. That is, the maximum duration a packet can be buffered. Bytes in flight, congestion window CWND is internal to the TCP stack and not in packets. However, we can observe bytes in flight in the window scaling graph. When CWND itself is the limiting factor of transmission, TCP is not hungry for data. The upper edge of the bytes in flight curve is approximately equal to the CWND size. The trend of the bytes in flight graph can be used to observe increases or decreases in CWND. BDP, bandwidth delay product, can be estimated by comparing the RTT graph and the bytes in flight curve. The point where RTT begins to rise above base RTT indicates that the pipe is full. At that moment, bytes in flight is approximately equal to BDP. Buffer size. In scenarios where the network bottleneck bandwidth and buffer size are fixed, for example, set by an administrator via QoS, the buffer size can be visually observed through the window scaling graph. When bytes in flight drops due to tail drop, its value is approximately equal to, in fact, slightly greater than, BDP plus bottleneck buffer size. If the traffic is in a competitive environment, the maximum buffer size it occupies changes dynamically, but its variations can still be visually observed through the window scaling graph. Send rate, visible in the TCP throughput graph. This is the rate the sender transmits. It is the amount of data the sender actually transmits per unit of time, regardless of whether it has been acknowledged. Delivery rate, visible in the TCP goodput graph. This is the rate of successfully acknowledged data. Bottleneck bandwidth can be observed in the throughput graph. Once the pipe is full, when RTT starts to exceed base RTT, the sustained goodput represents the bottleneck bandwidth. We place the Wireshark graphs side by side with the network congestion model on the left. The graphs on the right may appear relatively small. Next, we will go through how to observe each key parameter in Wireshark again, briefly. Be noted that the observation point for all the above parameters should be on the sender side. This means you need to analyze packet captures taken on the sender side. For performance analysis, in many cases where precise calculation isn't required, just observing send rate, delivery rate, RTT, and bytes in flight is enough to make a diagnosis. You can also use the I/O graph to plot RTT, bytes in flight, and send rate together in one graph. We'll dive into that later. So folks, our network congestion model is not just theoretical, not some castle floating in the air. It is a tangible, visible, and usable tool. How do we use this model to diagnose a real transfer? Now let's apply this. Here's a classic example. You log into an Ubuntu server to download a large file. The TCP algorithm is cubic. The network is clean. There's no loss, no competing traffic. RTT is less than 1 millisecond. Bandwidth is 10 Gbps. By all accounts, this should be fast. But in reality, the throughput never gets high. The engineers go around in circles. The network team says, I'm not dropping packets. The systems team says, no errors on my end. The application team says, the application is fine. Is it a ghost in the machine? No. There are no ghosts in networking, only patterns we haven't recognized yet. And when we use our network congestion model to observe, the story becomes crystal clear. Let's quickly revisit the 3 phases of network congestion model. If you're already familiar with this part, feel free to skip ahead. First, application limited. In this phase, bytes in flight is less than the bandwidth delay product, or BDP. The round-trip time, RTT, stays right at its base value. It doesn't fluctuate with bytes in flight, it just remains flat no matter what. And here, send rate equals delivery rate, meaning everything sent is being acknowledged promptly. The bottleneck, it's not the network, it's the sender itself. The application simply isn't feeding data fast enough. Second, bandwidth limited. Now, bytes in flight is between BDP and BDP plus the buffer size. At this point, RTT starts to rise because the pipe is filling up. Send rate becomes greater than delivery rate. You're sending faster than the network can fully acknowledge. Critically, RTT and bytes in flight now move together. As bytes in flight goes up, RTT goes up. As bytes in flight dips, RTT dips. They're synchronized. Third, buffer limited. Here, bytes in flight exceeds the total capacity of the pipe plus its buffer. RTT hits its maximum, it peaks, and then packets start getting dropped. That's the sign you've overflowed the bottleneck buffer. So, our mission is clear. We're going to find out which of these 3 phases this slow transfer is stuck in. Here's a challenge for you. Pause the video, download the PCAP file from the comments, and analyze it on your own. Then come back and continue watching. All right, let's open the packet, capture, and analyze it to find the cause. This capture was taken at the sender side. Remember, for performance analysis, you must always start from the sender side. Otherwise, you can't see the real behavior of bytes in flight. We don't need to look at every packet, just 3 graphs. Graph 1, RTT graph. Go to Statistics, TCP stream. Graph, round trip time graph. Here's the RTT graph. What do we see? RTT is completely flat, steady at around 1 ms, no increase, almost no spikes. What does this tell us? The buffer is not queuing. If there were a queue building, RTT would rise. Flat RTT means no buffer occupancy. Graph 2, bytes in flight graph. Now switch to window scaling graph. This is bytes in flight. Data sent but not yet acknowledged. Look at this. The bytes in flight line is stuck on the ground. It never takes off. The maximum? Around a little more than 60 kilobytes. Here's a critical observation. Bytes in flight remains a flat line. It doesn't grow, and it repeatedly drops to 0. Also, notice that RWN is much larger than bytes in flight, so TCP flow control is not the limiting factor here. Graph 3, throughput graph. Now switch to throughput graph. Look at send rate, what the throughput line shows, and delivery rate, what the goodput line shows. They're almost tightly coupled, hovering around 250 Mbps. They never go higher. The rates just never climb. Now let's put all 3 graphs side by side. We have 3 pieces of evidence. First, RTT is flat, no queuing delay. This rules out bandwidth limited, let alone buffer limited. Both of those would show rising RTT. Second, bytes in flight is just a little more than 60 kilobytes. It's a flat line that never grows and it repeatedly drops to 0. Combined with RTT staying at base RTT, This means bytes in flight is below BDP. It never grows to reach BDP. The pipe isn't full, not even close. Third, send rate equals delivery rate. This means the network is delivering everything the sender transmits. It's clear. The bottleneck is the send rate. The network is delivering everything the sender transmits. It's just not transmitting much. Now, look at our model. Which phase matches all three? Only one, application limited phase. So what does all this tell us? Not a bandwidth problem, not network congestion, not receiver window limiting the flow. The sender itself isn't feeding the pipe. The transfer is application limited. Now things are clear. The whole transfer process is stuck in the application limited phase. The send rate is not filling up the pipe, and bytes in flight remains consistently below BDP. This transfer is a textbook example of the application limited phase. Bytes in flight is being held down and can't grow. We need to go deeper. Now, what does this remind you of? That's right. You're probably thinking of our network path model. Let's revisit it. From the TCP end-to-end perspective, 4 valves determine the maximum possible bytes in flight at any given moment. Bytes in flight is less than or equal to the minimum of 4 values: the send buffer, the congestion window, the receive window in BDP, plus the bottleneck buffer. It means the smallest of these 4 sets the hard ceiling. No matter how big the others are, bytes in flight can't exceed the tightest valve. And the 5th factor, feedback signals, determines how high bytes in flight can actually rise in reality. Feedback drives the dynamics. The valves define the ceiling. So first, let's check whether any of these 4 valves is the limiting factor, and then look at whether the form of feedback signals has affected the increase of bytes in flight. In our earlier analysis, we already know the receive window much larger than bytes in flight, so it's not a constraint. Bytes in flight is below BDP, so BDP plus bottleneck buffer is even less of a constraint. Now look at CWND. The congestion control algorithm is cubic. Normally, you'd expect to see slow start's exponential rise, or the characteristic cubic curve. But here, bytes in flight never even takes off. In other words, the cubic algorithm actually provides enough room for bytes in flight to increase, even though we can't see it directly in the packets. Here's a cubic curve for comparison in a scenario with fixed available bandwidth, fixed buffer size, and tail drop. In it, you can see the slow start curve and the periodic cubic curve. Clearly, in our current case, bytes in flight does not grow in line with cubic CWND. All right, among these 4 valves, send buffer, CWND, RWND, BDP plus bottleneck buffer, we've ruled out 3. That leaves only 1, the send buffer. So is the send buffer suppressing the increase of bytes in flight? Let's check. Using the command sysql, we can see the TCP send buffer settings on Linux as follows. The 3 values represent minimum size, the minimum amount of memory TCP guarantees for the send buffer, even under memory pressure. Default size, the initial size of the send buffer when the connection starts. Maximum, the maximum size the send buffer can grow to. On Linux, the default is 4 megabytes, famously known as the 4 megabytes curse for long fat network. In our system, we've raised it to about 2 gigabytes. This means the send buffer is not restricting bytes in flight. There's plenty of room for more data. Therefore, send buffer size is also not the limiting factor for bytes in flight. Now all 4 valves have been ruled out. Let's also check the health of the feedback signals. Fully explaining the health status of ACKs is not something one video can cover, but we can briefly discuss the state of ACKs in this case. The smallest of the 4 valves is equivalent to the speed limit on a road. Can we drive fast enough to reach it? It all depends on the health of the feedback signal. If the road conditions are good, we can reach the allowed speed limit. If the road conditions are poor, even if the speed limit is not low, we cannot reach it. First, observe the RTT graph from the receiver side. Here, the RTT graph no longer represents RTT, but ACK delay, the time between the receiver receiving data and sending ACKs. You'll notice the RTT line is close to 0, very small, and very stable. Compare this with the RTT graph from the sender side. The sender side RTT line is also very stable. This indicates that both the forward path of data packets and the return path of ACKs are very stable. There are no errors, queuing, dropping, or other factors that might prevent bytes in flight from fully utilizing the ceiling provided by the four valves. That means all four valves and the feedback signal status have been ruled out. Nothing in the TCP stack or network is preventing bytes in flight from growing. If TCP and below are cleared, then the problem must be above TCP. Think about what we can learn from this case. When analyzing any TCP-based performance issue, the best troubleshooting order is not to go top-down or bottom-up through the TCP IP stack. My recommendation is always to start with the TCP layer. There are two reasons for this. First, TCP serves as a perfect dividing line for network troubleshooting. If there's an issue within the TCP layer itself, or if its behavior reveals problems in lower layers, that's something to hand off to the system engineer or network engineer for deeper investigation. Conversely, if the TCP layer looks healthy, it means the underlying path is reliable, and the problem is more likely to reside in the application layer or a higher level protocol. At that point, we should shift our focus upward. Second, Wireshark comes with a highly practical and effective set of TCP troubleshooting tools built right in, namely the TCP stream graphs. These provide 5 different graphical perspectives, and when combined with our models, they help us quickly assess the health of a TCP connection. For this particular case, by using the network congestion model and the network path model, we've ruled out the network itself and any TCP end-to-end limiting factors. TCP and below are completely cleared. The models simply draw the line. If you're a network engineer, here's what this means. You can now confidently walk over to the systems or application team and say, "The network is fine. Your side isn't sending data fast enough." For system engineers, you'd also know TCP itself is not restricting the transmission. Then you can focus your precious effort in the right troubleshooting direction. That's not blame or finger pointing. That's clarity. That's a clear responsibility boundary. And that's a huge step forward in troubleshooting efficiency. It simply cuts the loop of the blaming game. This is the power of the two models. It's logical. It's evidence-based. It doesn't rely on guesswork. It gives you deterministic answers, not vague, unrepeatable experience. With a model-driven methodology, when you open Wireshark, you no longer see random noise. The packets tell the story. The models help you read the DNA in it. And once you see the truth, you can't unsee it. Throughout this case analysis, we've walked through each limiting factor step by step, and it may have felt a little lengthy. But in reality, once you become proficient with these models, these judgments happen in an instant. You'll be able to see through to the truth at a glance. And could we go even deeper? Absolutely. Why is the application not sending faster? Is it disk I/O, application logic? Network analysis and Wireshark could do more. That's what we'll cover in future lessons to find the root cause. But for now, it's good enough. We've used the models to pinpoint where the problem lives. All right, now let's recap what we've built together in the last 4 episodes, which is part 1 of our network congestion and bottleneck series. From TCP's view, the entire network path simplifies to a single pipe. At any given moment, there is one bottleneck in each direction. It controls the flow, forms queues, and caps throughput. The entire complex path reduces to a single pipe defined by 4 key elements: base RTT, bottleneck bandwidth, buffer size, the bottleneck devices, queuing and drop policies from TCP end-to-end view. The smallest of the 4 valves determines the maximum possible bytes in flight at any given moment. Send buffer, CWND, RWND, BDP plus bottleneck buffer. A 5th factor, feedback signals, determines how high bytes in flight can actually rise in reality. From application end-to-end view, transmission performance depends not only on the TCP pipe itself, but also on factors above TCP, namely host system limits and application limits. When we fill the pipe and analyze the transmission, we can abstract the dynamic interactions into a simplified network congestion model, a model that describes the crucial behavior of any end-to-end transfer. Every TCP connection at any given moment exists in one of 3 phases: application limited, bandwidth limited, buffer limited. There are only three ways a flow, specifically its bytes in flight, can be limited. A slow transfer always gets stuck in one of these three phases. By watching bytes in flight, RTT, send rate, and delivery rate in Wireshark, you can diagnose the phase instantly. These two models, the network path model and the network congestion model, are your foundation. They are how you truly understand what congestion and bottleneck actually mean. These two models were inspired by the original BBR paper from Google's BBR team, combined with the practical visualization tools in Wireshark and its measurable parameters. The network congestion model, in particular, extends the BBR paper's diagrams of bytes in flight, RTT, and delivery rate by expanding their parameters and adapting them to the practical observability capabilities already available in Wireshark. Special thanks to Neil, the Google BBR team, and Gerald Combs, the creator of Wireshark. Your pioneering work made this course possible. In the next episode, we'll set up your lab environment hands-on, giving us a controlled, reusable setup capable of replicating almost any network scenario. Then we'll take these models from theory to reality even deeper, with live captures, real packets, and surprising insights. Trust me, once you see the truth of the bottlenecks, you'll never look at Wireshark the same way again. If you want to move from just seeing packets in Wireshark to truly understanding the story they tell, this series is for you. Hit subscribe and turn on notifications. Network analysis is not magic. It's not about gut feelings or 10 years of experience. It's a repeatable, verifiable methodology. We're just getting started. I'm Tai Fung, and I'll see you in the next episode.